Okay, so in this video we're going to look at proof by induction, and we're going to focus on proof by inductions for iterative sequences, so where each term is defined by the previous term or potentially by the previous two terms in more difficult questions. So in this example we're going to look at, we're told that un plus 1 is 3 times un subtract 2. That's telling us that each term is 3 times the previous term subtract 2. And we're also told the first term is equal to 2. When we're doing these proof by inductions, your layout needs to be spot on, what you're writing needs to be spot on. So we'll go through that really precisely, but you need to make sure you're using the same wording here. So in any proof by induction, I'm always going to start, even though we're told it in the question here, I'd always start just by writing down very explicitly what our claim is. What we're hoping is that un is 3 to the n minus 1 plus 1. It helps just separate in our heads the difference between what we know and what we're hoping to show. This is what we're hoping to show. Okay, first step of a proof by induction, once we know what our claim is to look at the base case. So we know it works for at least one term. It's kind of the first domino falling over we're looking for here. So in our base case, we're hoping this is true for all terms. So for n greater than or equal to 1. So the base case, we're going to consider n equals 1 and hope it's true for n equals 1. If it's not true for n equals 1, then there's no point doing it for the rest of the terms because we don't even have a start. So I'm going to use LHS and RHS to represent left-hand side and right-hand side. These are common enough that you can just use these terms. So the left-hand side of our claim is just what happens when we replace n with 1, which is just u1. And we're told in the setup up here that u1 is equal to 2. So the left-hand side of our claim is equal to 2 when n equals 1. The right-hand side is what's going to happen if we replace 1 in that 3n minus 1 plus 1, the right-hand side of our claim. So if we do that, we get 3 to 0 plus 1, 1 plus 1, which is equal to 2. And okay, we should be relieved because we're getting our right-hand side and our left-hand side equal. So we're just going to say something to that effect. So the left-hand side equals the right-hand side. So the claim is true when n equals 1. You need to make sure you're writing this. So you can say for n equals 1 if you want. I'll probably use when and for interchangeably, but you need to be stating the claim is true for n equals 1 or when n equals 1. Now we've got that, we get to the inductive step. This is where it gets a bit weirder. We're going to say, let's suppose the kth is true for n equals k, that the kth term is correct, and then see what we can say about the k plus 1 term. So this is getting to the point where we want to show that if the kth domino falls over, then the k plus 1 domino falls over as well. If we get that alongside our base case, it's going to tell us every domino is going to fall over, i.e. our claim is true for every single term here. So at this point, we're going to assume the claim is true for n equals k. It's essential here that you write that as it is, not writing assume n equals k, which might feel is saying the same thing, but assume n equals k is saying we're assuming something about the value of n. Here we're assuming something about the veracity of our claim for this given value of n. And let's say very explicitly what I mean. So that is, what are we assuming? Well, that's if we replace n with k in our claim. So we're assuming that uk is equal to 3 to the k minus 1 plus 1. And now we want to consider the next term. So we're going to consider n equals k plus 1. This next step is for us rather than for the proof, but we need to work out what we're about to target. So our target here, make sure if you are writing this, which I recommend you do, make sure you explicitly label to the target because we don't know it yet. But our target's going to be what happens when we place n with k plus 1 in our claim. So we're hoping that uk plus 1 is equal to 3 to the k plus 1 minus 1 here. Yes, we could write 3 to the k plus 1 minus 1 as 3 to the k, but we want to really explicitly replace n with k plus 1. And there's some mark schemes that will penalize you if you don't do that explicitly. Okay, so that's what we're hoping for. So let's start with the left-hand side there. So the left-hand side of our target is uk plus 1. Now, what do we know about that? No, that target's saying what we're hoping to prove, but what we know is what was given up here in the way the sequence is defined. If un plus 1 is 3 un minus 2, then uk plus 1 is 3 uk subtract 2. We know that for absolute definite. Sorry, my pen just went a little bit weird there. Okay, now we're ready to make use of our assumption. We've assumed something about UK already, which is going to be useful. We've got this thing here. We've assumed that UK is 3 to the k minus 1 plus 1. So let's make use of that. Let's say we can replace this with 3 to the k minus 1 plus 1 subtract 2. This is what we're going to call our inductive step here. Okay, so there's not much sensible to do apart from just expand the brackets here. Now, 3 times 3 to the k minus 1, this is 3 to the 1 times 3 to the k minus 1. So adding our powers, we're getting 3 to the k plus 3 minus 2, or 3 to the k plus 1. Have I made an error in here? Oh no, we're all good. Sorry. So we've got this. Now let's look at the target. Apologies, I've just made a mistake in the target we've written. That target there should have been a plus there. I'll cause confusion there. Apologies about that. So now we've got to this left-hand side. We've got 3 to the k plus 1. This is basically what we want as our target. Let's just explicitly write that in that form. And we've got this. This is exactly what we were hoping for. So we've shown what we want. So what we've shown now is that if the claim was true for n equals k, if we were correct, if we were okay in assuming that, then the claim is going to be true for n equals k plus 1. So this is where we just need to write our conclusion, but the conclusion needs to be really clear. So first sentence of the conclusion is, so if the claim is true for n equals k, then the claim is true for n equals k plus 1. Note, we're not saying the claim is true for n equals k and n equals k plus 1. We're just saying if it's true for n equals k, then it's true for n equals k plus 1. And now we're going to say, since the claim is true for n equals 1, we're now able to say, well, it must be true for all of them. So the claim is true for all positive integers n. So that's all the bits you need to your proof by induction. Obviously, there's different sorts of proof by inductions that will come up, but there'll be different videos going up for those. So just as a quick summary of how we're going about here, start by stating your claim. That's really for you to go back to and remind yourself of what you're trying to prove. Get your base case, so whatever the first value of n is. Most of the time that's going to be 1, but just make sure you look at the question. Show your left-hand side and your right-hand side are the same when n is equal to 1, and conclude to that effect. Then state we're going to assume the claim is true for n equals k. Again, be careful with your wording there, not just saying assume n equals k. And say what that means when we replace n with k, and that's just replacing in our claim n with k. We're then going to consider n equals k plus 1, and like I say, this target is just for us to know where we're aiming. So if you want to decide somewhere, fine, but as long as you label it with a target, you're fine to state it. Apologies, that's where I messed up on putting negative subtract 1 earlier on. And then we're looking from the left-hand side of our target, using what we know about the sequence, and then using the assumption we made, and we can rewrite it as we want. And then that's the conclusion to finish off with. Okay, thank you very much.